Here is a question. Read it carefully and think about the answer. Let us solve it step by step. Let us first understand the key concept here. Catalytic hydrogenation of an alkene adds H2 across the double bond. If the hydrogenation creates one or more new stereocenters or reveals existing ones, the product can exist as cis and trans diastereomers. Analysis of each option. Option A. H to C is equal to attached to a cyclohexane ring that also has a CH3 substituent for methylmethylcyclohexane. The exocyclic double bond H to C is equal to is between the ring carbon and an external CH2. Hydrogenation of this exocyclic double bond converts H to C is equal to into H3C, giving methylcyclohexane with a CH3 at C1 and CH3 at C4. This produces 1,4-dimethylcyclohexane, which can exist as cis and trans isomers. So option A gives cis and trans products. Option B. A cyclohexene ring with CH3 groups at two positions, 1-methyl-4-methylcyclohex 1-Na or similar, i.e. 1,4-dimethylcyclohex 1-Na. Hydrogenation of the endocyclic double bond gives 1,4-dimethylcyclohexane, which also exists as cis and trans isomers. So option B gives cis and trans products. Option C. A substituted cyclohexene with stereocenters already shown. The structure shows a cyclohexene with CH3 on the double bond and existing stereocenters at ring carbons with specific CH3 configurations. Hydrogenation of this alkene introduces a new stereocenter at the formerly sp2 carbon and combined with the existing stereocenters, both facial additions are possible, giving diastereomeric, cis and trans, products. So option C also gives cis and trans products. Since all three structures, A, B, and C, upon catalytic hydrogenation produce products with cis and trans isomers, the answer is D, all of these. Why other options fail? Options A, B, and C individually are correct, but since all three satisfy the condition, option D is the most complete and correct answer. Therefore, the correct answer is D. Therefore, the correct answer is option D.